All right, we're looking at page 166, number 8. And these are our linear programming problems. This one's kind of nice here. It actually tells you what your variables are already. Suppose that you go into business raising thoroughbreds and quarter horses. Having studied linear programming, you decide to maximize the feasible profit you can make. Let X be your number of thoroughbreds. And let Y be the number of quarter horses. I'm writing those down right here. I'm already thinking that we're going to have some restrictions on this. It looks like your supplier can give you at most 20 thoroughbreds and at most 15 quarter horses to raise each year. Well, we know it's not reasonable to have negative thoroughbreds as well, so we're going to say that our X value has to be between 0 and 20 then. And then that our Y value has to be between 0 and 15. It says that we must raise at least 12 horses total each year to make the business worthwhile. So, the total number of horses is X plus Y. It has to be at least 12. So that means it has to be less than or equal to 12. Now it has a thoroughbred eats 2 tons of food per year, but a quarter horse eats 6 tons of food per year. You could handle no more than 96 tons of food each year. So, the thoroughbred X is 2 tons. This is the normal total amount of tons eaten by a thoroughbred, plus 6 tons per, or by all the thoroughbreds, 6 tons per quarter horse times some amount of quarter horses gives you, we want to make a number less than or equal to 96 tons of food. We also have that a thoroughbred requires 1,000 hours of training per year, and a quarter horse only needs 250 hours of training per year. You have enough personnel to do at most 10,000 hours of training per year. So, 1,000 hours per thoroughbred plus 250 hours per quarter horse has to be less than or equal to 10,000. I can tell you, looking at this, the only one that's not alike in terms of the size of the numbers to the last one, I'm going to reduce this right away. So divide by 10, 100x plus 25y is less than or equal to 1,000. Looks like I can divide by 25, 4x plus y is less than or equal. 1,000 divided by 25 is 40. So now it looks much more reasonable for when we go ahead and graph a feasible region. So I'm not drawing the negative quadrants because we already know that we're going to be between 0 because we can't have negative horses. So we're going to be in the positive quadrant, quadrant 1. So this is our number of quarter horses. And Y is our number, or sorry, X is our number of thoroughbreds. We have our X values between 0 and 20. So here X value is bigger than 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm pointing the arrow inside because we know we want to have less than or equal to 20 of them. Then we know 15 quarter horses is the max. 3, 4, 5. We know because we have to have more than 0 of them, this box is our initial feasible region. But now we have x plus y has to be less than or equal to 12. Now, do you know what? I'm actually not so certain about that equation. I think I made a mistake. I'm going to go back and check. You must raise at least 12 horses. At least is greater than or equal to. So that's where my first mistake is here. So we have x plus y is greater than or equal to 12. So, because we could have more horses, but the smallest amount we could have is 12. So 12. Oh, sorry, this is me doing this in standard form. The x-intercept is when we make y 0, so that's 12, 0. And then our y-intercept is making the x 0, 0, 12. So then we go ahead. Give me 1 second, I'm going to use a straight edge on this. Now we have that we have to have greater than 12. So we plug in 0, 0. We're going to see that it doesn't work. 0 is not greater than or equal to 12. So we shade away from 0, 0 in this direction. Then, so we've graphed this part, and this part. We next have 2x plus 6y equals 96. Divide that by 2 right now because it's going to be simpler. So we have x plus 3y is less than or equal to 32. Sorry, 48. So then, when we go ahead and we graph this one, we have 2 points. We have 48, 0. The x-intercept, and then the y-intercept, 0, 16. 48, 0 is like way out here. I'm not even worried about that. And then we have 16, sorry, 0, 16 is right here. I have no desire to draw 48 coordinate points here. What I'm going to do instead is take the slope. So the slope here is the opposite of a over b, so it's negative 1/3. We're only talking about this equation right here. That's the only one we're talking about right now. So from here, being our y-intercept, we can go down 1 over 3. Down 1 over 3. 3, 6. Down 1 over 3, over 9, and then to 12, then to 15. Now, we see all the challenges here with getting this completely accurate. 12, 15, 18. This is why we always have to algebraically find these at the end, because there's going to be mistakes. Especially with this many graphs. Now we want to see if 0, 0 is a possibility here. 0 plus 0, 0 is less than or equal to 48. That's true. So we're shading towards 0, 0. That means this triangle just got cut out of what our possible answers are. We're only in this. It appears to be a hexagon that's a little oblong. And then we have our last graph of 4x, our last equation, 4x plus y is less than or equal to 40. That gives us the 2 points, 10, 0, and then 0, 40. Once again, I have no interest in graphing that, drawing that many points for it. I see 0, 10, it's right here. Or, sorry, 10, 0, it's right there. I need to find the slope. So the slope is always the opposite of a over b in standard form. Divided by 1 is still negative 4. So we could go down 4 over 1 this direction, but it's going to be more beneficial for us to go up 4 over 1. Now, go up 4 this way in the negative direction 1. So that gives us 9, 4.
I don't know if that intersects or not. Then that gives us 8, 8, 7, 12, 6, 16,
Now, the really important part with this is to know which portion we're going to be finding our possible solutions at. We're going to be finding on this side or this side. Now, in test 0, 0 in this situation, 0 plus 0, 0 is less than or equal to 40 is true. So our solutions are only going to be here. This is our feasible area. Now, we want to see which ones are our maximum or our minimum. We can go ahead and find each of these points. These ones are a little bit easier. We have 0, 12. We have 0, 15. We have this point here, which we know the y value is 15. To get the x value, we have to plug it into this equation, which off the top of my head, I'm not positive which one it is. Oh, I think it's this one right here with 0, 16. So we plug in 15 here. So we have 15 for y, so we have x plus 3 times 15 equals 48. The x is 3. And then we have over here the intersection of these two lines. This one, once again, is the 4x plus y equals 40. So you're going to go ahead, for this one, you have to take the two lines, 4x plus y equals 40, and then x plus 3y equals 48, and you're going to have to go ahead and solve that system. Let's see here. Multiply by negative 4. So that'll give you negative 11y, 120, 144. I'm doing this without a calculator in my head, so it's not going to be accurate. Let's see here. Let's multiply this one by negative 3. Negative 12x minus 3y equals negative 120, and then negative 11x equals negative 72. You hear the bell just rang, so we're going to have some problems there. This should give you a good start on the direction that you would head with this one.